Yeah. Okay. Good morning, students, and thank you, Manshu, for the introduction. Yes, today we are going to talk. I think you people, you students already have gone through various sessions of, on space science and its requirements, why we need to do a space exploration. So today our topic is, the mission design for the space exploration. What we mean by mission design? So I'll be trying to cover a few of the aspects, not going too technical, but yes, how it needs to be with the mission objectives, how we need to start a particular mission, and then configure it and realize it and maintain it in orbit. So, okay, this is my first slide. Just I wanted to start with our great history. We know that India has a great and ancient civilization with medical text dating back to 800 BC. Indian astronomy was at its peak in the 5th century under the greater astronomer and mathematician Aryabhatta. He figured out that the Earth revolved around the sun some 1,000 years before the Europeans did it. But yes, we know waves of invasion and colonization led to some decline of science in India, and not until independence in 1947 was we able to make a fresh start. And then for Indian space program, the story goes right back to 1960s under the vision of great physicist Dr. Vikram Sarabhai. His vision of using space technology to solve the real problem of man and society. But then, at that time, it was not an easy task to convince the government of the day about the relevance of the space program for a developing nation. Eventually, with all his possible efforts, he succeeded in obtaining the funds for the space program, and that was when the Indian space journey began with the vision of harnessing the space technology for national development and parallel while pursuing space science research and planetary exploration. So I'll be just covering few of the interplanetary missions because the topic is, today's topic is only talking about the interplanetary mission. So I'll be covering the mission objectives of an interplanetary mission. So we know that there are, for us, many of us, we will be just, wondering why, first of all, we have to either go to moon, go to Mars, doing all space explorations. What is the need for all this? And how this, all these needs, how the mission objectives are derived. So first, let us talk about moon. So, why we should go to moon. So they see, actually speaking, there are many unanswered questions still about moon. So earlier, before we launched, Chandrayaan 1, there was a question that whether there is a water on moon, and then also some of the lunar rock samples which were brought by Apollo mission at that time, they indicated the abundance of helium on the moon. And then and we all know that is a helium is as a fission fuel. We can generate, it can be used as a important fuel for power generation in future. If we are able to harness that material and helium, if we can bring back, it will really be a very, very important fuel in future. So this is one of the important, many like that, expanding knowledge about the origin and the evolution of moon. Similarly, doing this resource mining, getting helium. Apart from that, it is one of the other important things when we do such missions is, improving the quality of life on Earth itself. I will give you an example. A computer algorithm which was developed for one of the space programs, such space programs, then it was applied to X-ray images. It did a better job in detecting the early stages of breast cancer than the conventional method. So, this cross-pollination of fields, innovation in one, bringing the revolutionary changes in another, it happens all the time. And yes, it undoubtedly improves the quality of life. And then the main reason of such missions is, to inspire the next generation of space explorers like you who can contribute to the future growth of a nation. So that is how our mission to moon, the objectives were derived from all these reasons. And then we had a very successful mission, Chandrayaan 1. Chandrayaan 1 was the first mission in which we had which is the satellite where it had to go beyond the Earth's regime, about 3 lakhs kilometer distance away, because till that time we had the satellites which were revolving around the Earth, and they were either doing some remote sensing applications, or they were communication applications. But Chandrayaan 1 was the first mission which was going beyond those earthbound missions and reached moon. It was a very successful mission, and as I told, we can see that some of the important achievements of Chandrayaan 1. You can see it was like, discovery of water. You people all must be knowing the first time the Chandrayaan 1, the payload on Chandrayaan 1 was able to detect the presence of water ice on the south pole of the moon. And then first time, yes, we had a mission which was which had done lot of moon mapping, mapping of the surface of the moon, finding where the craters are, what type of craters, what type of boulders, how the moon surface looks like, how this data can be utilized for further lunar landing missions. So all those achievements, it really was a great achievement for Chandrayaan 1. And in this figure, if you can see down, there's a big antenna. First time we have established the Indian Deep Space Network, which is called IDSN. And it has 32-meter antenna, 18-meter antenna, huge antennas, which are very much required to communicate when the satellite moves into the deep space. So these were the main achievements of this Chandrayaan 1 mission. And apart from that, one picture I want to share with you. So this you can see that we had a moon impact probe. First time, it was not a soft landing, but yes, the probe was separated from the satellite after reaching the moon, and it was near the Shackleton crater. It impacted the lunar surface with the moon flag, with the Indian flag on its surface, on its face. So this is the first time any probe impacted from Indian mission from ISRO, and this is also was one of the great achievements of Chandrayaan 1 mission. Apart from that, as we do one mission, we lay a strong background for another mission. This mission helped, in that time, this mission helped to understand the lunar surface, a much detailed way. We had the payloads which were taking images of full moon surface, providing the digital elevation maps, stereo images, how the craters, what the surface looks like, how deep is the, how the terrain features. All we were able to make map of full lunar surface, and which really provided a good database and good background to know for the landing mission where we should go and land. So this is a very important mission which really provided the inputs for the next mission. Now coming to the next important thing. See, this is I just told why we have to go to moon. I'm just trying to first cover that, what are the basic requirements or the basic need of going either moon or Mars. So let us say after moon, then why we have to go to next, question will come, why we have to go to Mars also. When we have reached moon, okay, then why further beyond, why we need to go to Mars? We all know that Mars, again for Mars also there are many, still we do not know very many details about Mars. There are very many unanswered questions about Mars. Still the thing comes whether there is a life on Mars, or there's a water on Mars, whether colonization is possible in future on Mars. I like to share with you very interesting fact about Mars. Billions of years ago, when our planet was just a ball of molten iron, Mars seems to have been a planet that had abundant amount of water on its surface, a sufficiently thick atmosphere capable of supporting the life. So, over a period of billion years, while our planet grew to be nourishing for life, Mars lost all its favorable conditions for sustaining life. So, what happened? How the life disappeared. Data about Mars can help us to understand how this happened and provide unanswered questions to some of these queries. So like this, there are so many aspects when we think about going to moon or going to Mars. And one more important aspect which I want to cover here, basically why we need to go either to moon or Mars. See, you see that in our solar system, we need to ensure that, we all know that where the life is sustainable, what is important to create to have a life is optimal temperature, the pressure, and the other essential conditions for survival. So in this zone, which we are trying to see here, that there is a zone which depicted in a green color. This is called the habitable zone. This habitable zone has, as I told, the surviving conditions for in terms of temperature or pressure, and that lies between Venus and Mars. So here, this also tells us that yes, when Venus can, we know, but when we go to Venus, Venus is very near, goes near to Sun, and then it will be too hot to survive. But Mars is again too cold to survive. But still, it is possible to survive on Mars. So that is the main reason of going first, reach moon, and then from moon. And anyhow, there is a, I will also cover some few aspects where we can see that moon can be taken as a gateway to further going to either to Mars or deep space mission. As we all know, moon is having 1/6 of the gravity of Earth. So anything, if we reach moon to go out of the energy which is required to go up out of moon surface is much lesser than the energy required when we start journey from Earth. So this the moon really is can be taken as a gateway for future deep exploration or deep missions. So now when we talk of this, these are mission objectives. When we go to moon, what we can get, and when we go to Mars, and then yes, beyond Mars also, people are talking about going beyond the interplanetary, beyond solar system and all that. So, but we need to take first steps. We need to start our journey first from moon, and then Mars, and then beyond. But then the important thing, what is there, how to go, what is the physics behind it, what the dynamics goes behind, how we can reach to moon or Mars. So that is where our important subject, I think you all people would have started, maybe not now, but you will surely come in near your next few years, you will learn that, there's something called orbital mechanics. Orbital mechanics means how it all deals with the, I am very sure that you people also would have heard, would have read about the gravitation force, the force of gravity, the effect of the gravity force, how a body moves in the field of sphere of the gravity. So this is what we cover in the orbital mechanics. So I will be just only covering few of the aspects of this orbital mechanics, mainly for moon and the Mars mission. Moon mission is basically, we know that moon is a satellite, a natural satellite of Earth. It is always within the Earth's gravity. We are not going beyond Earth's gravity. So this is something, a different mechanics which works for moon. But then if we talk about Mars, then we have to go out of the gravity well of Earth. So there is a different mechanics works for Mars mission or going to Mars. So let us see, you can, here I am just trying to see, discuss with you few of the aspects which are very important when we try to design a mission to go to moon or Mars. This is, I have just covered here, you can see some of the, orbital tracks of a Chandrayaan-1 mission, which is called flight path. So here what you can see, there's, Earth is here, and then we have around the Earth, we know there is a moon revolves around the Earth. So it is basically any problem when we study in physics or in mechanics, orbital mechanics, we know we have to see, what are the main central body, what are the secondary bodies. So here we have Earth as the main body, and then satellite, which is revolving, which is going to revolve around the Earth, is a secondary body. So this becomes a two-body problem. We have to solve equations of motion for this two-body problem, and then we have to raise that in for each orbit, we have to raise the height from the Earth's surface. You can see this itself is telling you it's an ellipse. I think you people also would have heard about elliptical orbit, where we have the primary body at one of the focus, and then the other body revolves around this in the elliptical path. So this is the distance which is very near to Earth. It is called perigee, and the distance which goes the other side with the highest, biggest, largest distance, that is called apogee. So this is how any body around Earth revolves with having a particular perigee and apogee. Now we have to go to moon. What is required to go to moon? We know that moon is away around, it is around 3,60,000 kilometers away from Earth. So slowly we have to raise. What we need to raise? We need to raise this height. Apogee means we have to give the energy to the satellite so that its height, and the energy with respect to orbital height increases, and at the distance when we reach near to the orbit, the final orbit, which we called as translunar insertion, TLI orbit, which we Dr. Praveen mentioned, we had this yesterday. So yesterday we had this maneuver where we achieved the path which will take the satellite to the highest, the largest distance near to the moon, reaching to the moon surface. And once we reach the moon surface, anyhow, we know moon is also revolving around this Earth orbit, around the Earth. So this, after reaching the moon, when satellite reaches the moon, so here you can see the satellite is reaching the moon, and then when it reaches the moon, and there will be another elliptical orbit. We have to achieve another elliptical orbit, which will not be around Earth, but which will be around the moon. So this is called, see, it goes and then it gets captured, because we know force of gravity, it is always attraction force. A body always attracts the other body. So the force of attraction which is working between the moon and the satellite gets attracted by moon, and it captures, it is called, we are capturing in the moon's orbit. It gets captured into the gravity well of moon, and then it starts revolving around the moon. And once it starts revolving around the moon, we have, like, there also the highly elliptical orbit, where the distance from moon surface will be around 18,000 kilometer, biggest distance, and then shortest distance can be of the order of 170 kilometers, 200 kilometers. Then we have to do what? We have to do circularization of this orbit, because once we have different cameras or different payloads or any other probes, they need to observe on the moon surface. For that, we need to go very near to the surface of moon in a circular orbit. So that is how the maneuvers are done. The energies are distributed such that the satellite goes in a circular orbit. So this is the basic. So what we see is main mechanics. What is working in class 8 or class 9 and class 10. What we study simply, two body problem, or equations of motion, and then the conic section. All these things you can see are getting utilized, or it is used in this designing the trajectory when we have to go from Earth to moon. And similarly, we'll talk about Mars also. So these all the things are an important. I know people are very interested, and see whatever you're studying today is going to lay a big strong foundation for you, because then tomorrow you're not only moon or Mars, you will be going to interstellar and all that. So these all things will really play an important part in your subject and studies. Now coming to the next, I would like to just cover, and not only here, okay, some few of the figures which I wanted to say. If you see here, this is something called, what I talked about, the gravitational gravity well, or gravitational force, what is imparted, it is working between the two bodies. So here you see this is basically, there's an orbit where this white color, where the moon is revolving around the Earth. And then I told this orbit where it slowly satellite moves and goes near to the orbit of moon. And there's something called a sphere of influence. You must be wondering that, when Earth is putting a gravity force, how the moon is able to pull it so near, and then it is stopped rotating as a body around Earth, and it starts rotating about moon. So this is very important aspect. See what happens as the distance, you would have heard, that the force is inversely proportional to the r square, the distance square. So as we move away, the force of gravity reduces, but as we go more and more near to moon, its force of gravity increases. At a certain point of time, it is called the sphere of influence. Means that there is a distance around 66,000 kilometers, where if we reach very near to the moon by 66,000 kilometers, the prominent gravitational pull will be by moon and not by the Earth, because as distance increase, the gravity of Earth is reduced, but as we go near to moon, the gravity from moon is increasing. So once we reach to this sphere of influence, and then we have to get captured. See, what is more important is, let me see in this, yeah. In this one of the depiction, you can see it is coming, and then we have moon here. And here when, as I told, when the satellite is going near to the moon, there is a gravity force is working. And when any force is working, the energy also is getting imparted. Its velocity also increases. So what happens is, if the velocity of the satellite is increasing, it becomes such a more velocity that if we don't reduce the velocity of the satellite, it will just become a flyby. Means it will not get captured by moon. Even if the moon, the basic force which is used, which moon is imparting on the satellite towards itself, that force itself is imparting such an energy that it cannot sustain around moon. It will get to have a flyby. Means it can just go near and then go away in this white line. So it means that we need to have a maneuver which we call retro engines need to fire. They need to kill the velocity, they kill the kinetic energy of the satellite so that it can get captured around moon. This is also very important maneuver which we call lunar orbit insertion. And this ensures that we put a proper energy, and it's something, it is called like pushing the satellite into the gravity well of moon. That is what is achieved. And then you have, I told you, around 172 kilometers to 15,000 to 18,000 kilometer elliptical orbit, and then slowly we make it a circular orbit.
Yeah.
One so this is so coming to the next. So that is what important. Like I covered around, that what is going away from gravity, gravity of Earth, and reaching near the gravity of Moon. Similarly, we had Chandrayaan 2. This also had a similar flight path where we can see that we had many orbits around Earth, slowly increasing the apogee height, and then we achieved a trans-lunar insertion going near to Moon, and then getting acquired in the lunar orbit with the retro engines firing, and then getting circularized orbit around the Moon. Now, this is all we discussed about, between Earth and Moon, how the trajectory, how the mechanics works. Now, let us talk about beyond Earth's gravity. When we have to go beyond Earth's gravity, it is something called, when the previous problem is like a three-body problem. We had Earth, we had Moon, we had satellite. But when we tried to go to Mars, we had four-body problem. It is something called, Earth, we have Mars, we have satellite, and the Sun. So there are four bodies which we, all the, gravities of each other affecting the motion of each other, and how we can use those mechanical equations of motions and derive the flight path to go from any planet to any other planet. So this is something called interplanetary trajectory design. And very important for such missions is, we always know we have to, as I told earlier, we have to do some maneuvers, and we need to use propellant, fuel. So we cannot carry too much of a fuel, because again, if we carry more and more fuel, we will not be able to carry payloads. Payloads means we need to carry cameras, instruments, different probes, spectrometers, and so many scientific payloads which are going to do many science scientific operations. So to enable the having a good science, we need to see that we reduce the other mass requirement in terms of fuel or any other auxiliary requirements. So this is called fuel optimal trajectory design, where we have to do a departure. When we say departure, it means that we have to go away from the Earth's gravity field itself, and then we have to, once we leave the Earth's gravity field, it is like what? All our planets, like say Earth or Mars, they are rotating around Sun. So there is something, a very important central body. It takes place not only Earth, but when we leave Earth, our central body becomes Sun. Sun only is now putting, or the main force which is working on the satellite is from Sun. So now when it moves towards the Mars, it is basically in the influence of Sun's gravity. And once we go near to the Martian orbit, like this is the dotted line which I'm showing is the Martian orbit. When we go near to the Martian orbit, again I told you the sphere of influence will start working. As you go near and near to Mars, its sphere of influence will start pulling the satellite to itself, to its surface, towards itself. And there again, if I don't, because this is a very interesting phenomena. When we go, the gravity is pulling you, but because of the gravity, the energy which is given to, which is gained by the satellite or by the probe, it doesn't allow it to go around the Mars or around the planetary body. We have to necessarily kill the energy. So how you kill the energy? Again, you fire a retro rocket, and then the energy is reduced so that it pushes it into the gravity well of Mars. So that is how it is becomes a four-body problem. It is not remaining only two-body or three-body problem. It becomes a four-body problem. So this is very important, as I covered also earlier, the sphere of influence. Where we are near to Earth, we have a gravity pull of Earth dominant. When we are near to Mars, we have gravity pull of Mars is prominent, and when we are in between Earth and Mars, the gravity pull of Sun plays a role. So this is a very complex problem to solve. It's not just equations of motion of two bodies of like that. It's a four-body problem. So, but how we solved it? It is for us also. It was a very new thing for us to address, because we never did this type of equations of motion solving at that time. Then there is a method of doing that. This all four body problems, it gets converted to two body problem. I will just cover in my next few slides how we make it four body problem to two body problem, which we call as a patched conic method. I'm not going to too much detail. I just want to make aware of you that how the complex problems are solved by some methods which are simplistic methods, but yes, they're very important and very strong tools to solve such problems. So this is, I will not go much. See, when you say this patched conic, okay, now I understand that you people would have heard about conic problems like, a circle or ellipse, and then there is something called hyperbola. So if I go to my next, let us see this slide. So here you see there's a sun, and then we have Earth, and then we have Mars around the sun, the outer orbit. So suppose we are here, where satellite is rotating around Earth. If you zoom it here, so when you rotate around Earth, we are in the elliptical orbit. But when we give it an energy which pushes it out, like I told you, going away from the Earth's gravity. So this is something called the conic section gets opened. It's not no more closed orbit. It gets opened in this direction and becomes an hyperbola. So, you must be reading about hyperbola. So this is how good an hyperbola you have to achieve. What should be the direction or the inclination of this hyperbola trajectory so that we reach near Mars? That is very important. Now, once it becomes an hyperbola, if you see, this is hyper with respect to Earth. When we talk with respect to Earth, it is an hyperbola. But let us come back and our perspective, let us change with respect to Sun. So what was hyperbola with respect to Earth? It is basically an elliptical around Sun. It becomes an ellipse around Sun. If you close the orbit, it becomes an ellipse around Sun. Now this hyperbola, then it became elliptical. Once it became elliptical, then it will be traveling in around towards the Mars in elliptical orbit. Then when the Mars, we reach the Martian orbit, we are very near to Mars. Then let us zoom it here. So this is Mars here. So when we are coming, suppose let us say we are coming from this direction. This is an hyperbola again. It's an open orbit with respect to Mars. But then when we give we fire retro engines and then kill its energy, it again becomes a closed orbit around Mars. This is called elliptical. So now we say we have, this is called like working in ellipse, then hyperbola, then ellipse. This is called conic sections. First you work only with Earth two-body problem, then you work with the satellite and Sun two-body problem, and then you work with Mars and satellite two-body problem. So the four-body problem can be converted into two-body problem, and this conic trajectory can be formed for this interplanetary missions. So this is just covering, what type of energies are really required when we are in, we know our rockets will give the energy, and we also know what is the escape energy, what is escape velocity we have. So after the rocket, our PSLV, which injected the Mars Orbiter mission into the orbit, once it injects the orbit, it gives an energy, but that energy is not equal to the escape velocity. No, we have to escape. So the escape velocity of around 1.5 kilometers per second was required to make it in a hyperbola, which I was covering last time. So the previous slide. Once it becomes hyperbola, then again, once you reach near the Martian orbit, you have to again kill the velocity. So you need to fire retro engines, and then around 1 kilometer per second the velocity to reduce. So total energy which we need to give to satellite is around, the kinetic energy equivalent to 2.5 kilometers per second. That is how the, we have to carry the propellant which imparts this velocity in the Earth's orbit and in the Martian orbit. Okay, this is an important factor in the orbital mechanics for any mission, which is very important, is a launch window. It is not easy to launch any satellite or any probe at any point of time. There is a particular time, because how the time, just in this slide, I want to just cover a very small, initially how we make the launch window. See, suppose, you have sun here, you have Earth in the inner orbit, Mars in the outer orbit, and as I told, that we have this in between, which is something called elliptical orbit around the sun. So we have to leave the Earth's orbit, go to this intermediate orbit. This is called the Hohmann orbit. You will be reading further in your other for the top subjects, that how this orbit, which is called the transfer orbit, the Hohmann orbit. And then this Hohmann orbit joins the orbit of Martian at a particular point, and then it gets, again we have to impart energy so that it becomes the orbit same as the Martian orbit. So what happens is, we know that when Earth is here, Mars is somewhere, it is this is geometry. If you say Earth at departure point, and if we have to ensure that my trajectory, the cruise trajectory or the Hohmann orbit, it has to meet somewhere in the Martian orbit. But when it has to meet, it is not only it has to go into orbit. When I go into that orbit, that time Mars also should be there at that point. Otherwise Mars is rotating around the orbit. It is not there everywhere. When you reach at that time, the Mars should be there. So this is actually, if you say our Martian revolution time is every 1.88 years, around 1.8. So every 1.8 years, you will get a geometry where when you design the orbit, where it reaches at the point where at that time Mars also is there. So this is important. Actually, when you go depart here, at that time Mars is not here. Mars will be somewhere here in this point. Let us say here. So this is at something 46 degrees away, not 180 degrees away, but 46 degrees away. So what happens at this point, not at this orbit, at this point, somewhere here Mars is there. So the time Mars takes to travel and reach at this point, the same time the satellite also will reach and get captured. So this geometry takes place not every time. There's a particular time when this geometry occurs, when the Mars is just 46 degrees away ahead of Earth. So we cannot launch any time. We can only launch at the point when this condition is satisfied. So this is also very important part when you're designing an interplanetary mission. You need to take care of trajectory design. You need to take care of launch window design. And yes, this is very thing I wanted to share. Our Mars orbiter mission. With all these challenges, we could achieve this interplanetary, the cruise direction. I just told, the direction where you start traveling towards Mars. It was done successfully first time. Actually, before that, if you talk about the success rate of any Mars mission, it is less than 50%. And none of them till that time were able to do the first attempt when our Mars orbiter mission was planned. So, but our mission, yes, with all these trajectory design and all these mechanics playing role, everything, first time we were doing all that, but with all that, we could achieve this mission at the first time successfully. And this is like, as I told, the direction of cruise, where you need to start and you start moving towards Mars. If you can see how challenging it is, like suppose a golf ball is at somewhere here over Bangalore, let us say, and we have to go somewhere in California or somewhere in the US, it's so far, and the hole is there. So we have to, the golf ball, we have to hit the ball and it has to reach this hole in precisely go into the hole. And important thing is this, when you do this motion, the earth is also moving, it's a full sun is the earth is moving around sun, Mars is moving around sun. So all that, with all that movement, we have to ensure that this ball is going straight and going into the whole. So that is how that challenging it is to achieve this trajectory. Now coming to, when we talk of orbital mechanics, let us say further, come to satellite. Now what satellite carries? Satellite is to reach to the Martian orbit, as I told, the important, very, very important element, which is there, the propulsion system. As I told, that the energies which we are getting, either a boost energy or the retro energy which we are getting, is nothing from the propulsion system. And till that time, we had, basically you must be reading further in your course that, propellants are of many types. It's a monopropellant or a bipropellant. So the propellant which we use for interplanetary missions were bipropellants, and this propulsion system we utilized for many of our geosynchronous satellites, but they were perfected in performance by extensive amount of testing. Because first time we had to leave the gravity of Earth and reach towards Mars, and we had to travel a long distance, around 10 months of time, 650 millions of kilometers of distance. And the engine, we had only one engine. The engine which is used around Earth also needs to be used again, same around Mars also. So 10 months of time, the engine is.
Ma'am, can you just click on that one window is visible here?
Yeah, is it okay now?
Yeah, it is okay, yes.
Yeah. So what I was telling is the engine which we used, there was only one engine, and that engine was firing, as I told you, initially around the Earth's orbit, it was firing and taking the height, apogee increasing, that was working. And then for 10 months of time, that engine was in sleeping mode. And then when we reached Mars, it had to again reignite. Something like if you see in a car, if you keep for a long time, we will always have that, whether it restarts or not. So that also always, we need to ensure, we have to ensure that the engine, which is going to be in sleeping mode or in hibernation for 10 months, again, when we go near to Mars, the engine had to reignite and had to work as is required. But yes, we are very, the design of such a propulsion system was done first time. Design was similar to geosynchronous satellite missions, but the perfection, the testing which was done to ensure that it works in the deep space even after hibernation mode. So that was one of the important things which we need to ensure any propulsion system for when we go from any interplanetary mission. And then yes, this is the important thing. You may be seeing is a big dish. This is the antennas. They are the ear of the spacecraft. Anything if we have to send commands to or get the data from, these antennas only will work for us. They work as the ear of the spacecraft, as I told. So, but what is important, for any satellite, you need to have antenna. But these antennas, they have to respond to the distance of, you assume, like 220 millions of kilometers to 400 millions of kilometers. Its sensitivity, it has to be very, very finely tuned to respond to such a huge distance. It is like, a task of hearing a person's whisper across the soccer field. Such a sensitivity, but yes, the antenna was designed, it was tested, it was, and it worked full when the distance from the Mars was even 400 million kilometers, was also the antenna worked as expected. The design of this system also played a very important role. Then coming to the other important part of the satellite system is the power system. See, we know that for source of energy for us in such missions is only the solar energy, right? When we're in the solar system, we have the solar energy. Now the solar energy, we have to have solar panels which can generate the power. But the important thing is what, when we revolve around the sun, Earth revolves around the sun, there is a distance of 1 angstrom unit, what we call, and then there when we go away towards Mars, the distance increases. It goes like 1.5 to as I told in terms of million kilometers, 220 to 400 million kilometer distance. So the solar intensity reduces. The power which we can generate around Earth is almost half what we get in Martian orbit. But then the solar panels were designed, we need to take account of all those constraints. We need to design such that the panels can be used even in the near distance or even in the higher distance. How we do that? By properly offsetting the panel, not making the sun falling in the normal incidence when we are near to Earth, but when we go away from Earth to Mars, we can have an attitude or the orientation such that the sun comes normally incidence to the panel and generates required power. So these are the important thing, which is important systems which we need to really design for such a mission, for any interplanetary mission. I have just only covered a few systems, but there are many systems, very intricate things. The smallest things which we like, one of the smallest, a small part also that is design of a simple telemetry system. Telemetry means it's like the data which we have to, what data is coming to the satellite, and the telecommand, how we have to send the data to the satellite. All the digital aspects or digital engineering comes into important role in that aspect. So I'm not covering much detail, but there are many things which play a very important role in designing such missions. Now coming to very important point, that is apart from the system design or the trajectory design, the important thing is when we go deep into the space, we cannot, do a micromanagement of a mission. What do you mean by micromanagement? Like, any satellite around Earth, anytime, if we have to get data, we immediately point our antennas and get the data. Or whenever we have to send any command, we can just send a command to the satellite. When the ground station, we need to ensure ground station is there, and then at the visibility, when it comes, we can send the data command. But when we go to the deep space missions, this is not possible, because we know that there is light is having a speed of light. And when we say the round trip time, any signal, when you send to satellite and get it back, as you move more and more deeper and deeper into the space, the round trip time increases. It can go from 8 minutes minimum to 40 minutes for Mars mission, average of around 24 minutes, let us say. So such a, any signal if you send, it will take first 28 minutes or let us say 12 minutes to reach to Mars. Then from there, what has happened with that signal, what the command, what happened, get the telemetry back, again 12 minutes. So 24 minutes. You cannot, anything goes wrong at that time at the satellite or at the probe level, we cannot do any ground intervention. So we need to build the onboard autonomy. What is called is like, for such missions, this is very important, because we cannot have real-time operations. We cannot have visibility all the time. There will be always the data which we get and which we send is also limited amount of data. Then all those things makes it very impractical to micromanage. So what is the solution for that? The solution is have to have onboard software with extensive autonomous and automated functions. Okay, this is a plot just showing how the distance from Earth increases. It is simply, you also can make, when the putting the speed of light and see the distance increases, the round trip time also increases. So okay, this is around when we go around Martian orbit, the distance was around 200 million to 400 million, and the minimum distance can be 80 million kilometers. And when it is 80 million, your round trip time will be less of 8 minutes also. So then other important thing is, when why the autonomy is required. This geometry, if you see, sun is here, Earth is here, and then outer orbit, the Mars is there. Suppose there's a linear all the three, sun, Earth, Mars, they all come in a line, and then we call it a conjunction. And what will happen, any signal if you try to send to Mars, you cannot send because sun is coming in between. Any data you want to send from Mars to Earth, the satellite to Earth, you cannot send because again sun is coming. This is called blackout times. for any Mars, like a mission for Mars or so, this is always a time where we cannot communicate with the satellite. So this is something called blackout geometry. We have some 14 to 17 days of blackout geometry. Similarly, you can see in this geometry when we have Mars on the same side of Earth, again what will happen is Mars is sending data to Earth, but the background you have a sun. It's such a huge noise you will get from sun that the signal strength will reduce and we cannot, it's something called whiteout. Something if you're uh, in a vehicle, if you're driving and somebody's focusing, some focus is coming from the front, everything gets dazzled. So it is like we cannot communicate at that time also. This is called whiteout geometry. So all this during these times, during these, because of round trip time or whiteout or blackout, we cannot have micromanagement. So we have to have autonomy. So that is first time, for Mars orbiter mission, we had this autonomy built up. Basic thing is the system has to do self-diagnostics. It needs to keep seeing its own parameters and see that any system is going out of bounds. We should be able to reconfigure, go to the LLM system, and then so that the self-recovery also it has to do on its own. So this is what is very important for any interplanetary mission. Have a continuous watch, do a fault detection, do the isolation, and then reconfiguration without disturbing the prime function of the spacecraft. So this is the thing where the actual thing, the brain of the satellite, or you say autonomy. Full system is autonomous or smart systems. We have to build the systems for any space missions. And yes, with all this, Mars orbiter mission was, as all of you know, in 2024 September 2014, it successfully entered the Martian orbit. It was first mission which succeeded in its first attempt. It was the most economical project, all the interplanetary missions. It was a project which was realized in the shortest time of 18 months with so many new things, so many technical challenges. It could get realized in 18 months of time. It was the first Indian satellite having full-scale onboard autonomy. And yes, the youngest team worked for it. Apart from all the seniors and scientists and review boards, the youngest team worked for this mission. There are a lot of, this completed 8 years and it has sent huge amount of data. We have generated the full Mars Atlas, and the peculiarity of this Martian orbit was first time from our cameras we could cover the full disk of the Mars, and then various many features of, Martian Canyon around Wells of Mariners and the crater of the Huygens crater. Many features we could capture and made them our Mars Atlas. And this will really help now in future missions, to see where we can land. So once before a landing mission, we have to have a good understanding of those Martian, the planetary surface. So this really puts a foundation for the landing missions. Now, when we talk of landing mission, once it's Martian landing, now we are also talking about the moon landing. First, as I in the initial we told, no, we have to land on the let us say surface of moon. But for landing mission, it is a challenge is much more, because first of all we have to have, for example, let us say I will just take a case study which we are currently seeing, the landing on moon. So landing on moon, let us say we have to land near poles. Why near poles? Because we know Chandrayaan-1, we have seen that there is a presence of water ice on near the poles. So let us say, why not land near the surface at that near the poles? So then, when you decide to go near the poles, you have to find a suitable landing site. If you see here, this if in any surface near the poles will look like terrain features. So many will be the craters, the boulders, the elevation is so uneven around the surface. On that surface, you have to find the place where you can really, the flat surface or where the lander can land. It is a very challenging task to find near to the pole the landing site. So that we have to know. And also, when you have a landing site, you can see, there are some shadows because of the sun. If anything, if it lands in the shadow, we will not get sun energy. So we should not land in the shadows region. We should understand when we land, the shadows are not falling on the landing surface. Similarly, the communication, we should have a direct communication to Earth. We should not get blocked by any hill or any boulder or any such thing. So we should have a complete communication. And then, as I told, no, we have to land on where the sun is rising. We should have the solar energy to survive at that time. So, or that launch window gets limited. This is a very, very challenging, much more challenging than an orbiter mission. And apart from that, if we have to do autonomous landing, so it is like you are landing over unknown terrain. When, for example, now if any aircraft or airplane is landing, we have so many systems to support, where we should go. The GPS is there. There so many sensors are there to tell that which place to land, how to land, how much away you are from the landing track. But there, when we go to the unknown terrain, we have to know, we have to land without any assistance. It has to be unmanned landing. We have to have, for example, in the moon surface, we have to do a braking maneuver, because if you around the orbit is 1.6 kilometer per second velocity, that type of kinetic energy it will be having. So when we have to touch down, we have to reduce the energy to zero. So we have to use our engines, throttleable engines, which will break will put a brake on the craft, and it can land smoothly and softly. And then we don't have any GPS or SPS, so we need to depend only upon the instruments, the sensors, and the ranging data, the Doppler data. So those are the orbit determination. And at that time, when we do landing, we cannot even do any determination from Earth. So the sensors which we have to use on the lander, let us say, if we call it a velocity sensor, or we have to have a position sensor which can tell where you are, what is the velocity at the time of landing, and accordingly it will guide the probe to kill the velocity and then have a soft landing. Very important thing is, as I told in this figure, we have a very small place where you can, the error, if it cannot have an error, and suppose if you have more error, you can land up somewhere on the top of the hill or on the shadow region. We cannot have that type of landing. We have to have this is called error ellipse. So around the landing place, we have to have a very, let's say, within some few kilometers of distance, let us say within 4 kilometers, within 2 kilometers, and sometimes it becomes within few meters, we have to land. So those things are precise navigation. And then, yes, as I told, hazard detection and avoidance. Anything if you detect there is by landing, we have to see that where you're going to land, there is still will see very small borders. We should not land, because the craft should not topple when it is landing. So we need to ensure that there's no hazard. So those type of sensors we need to place and see that those sensors should help it to tell that where to land. So this is like, when we do a landing mission, so many challenges are there to ensure we have a soft and safe landing. And yes, when we land, we can go, we have near the poles, rich in minerals, water ice presence is there, we have more sunlit days, and we can do some in situ resource utilization, and think of this place, can work as a gateway to deep space travel. You must be knowing now the missions are coming, Artemis missions and many more missions which are planning to go near to the poles of the moon, utilize its resources, make the stations, the space stations there. And then from there we can take off to the deep space also, like a gateway to deep space travel. So with this, I conclude my talk, and yes, we are ready to take up any question and answers.